Hello, this is Sashidhar. I am from VIT Chennai. Today I am going to discuss about applications of finite automata in networking. Introduction to automata. Automata is nothing but a machine which accepts the strings of language over an input alphabet. There are four types of automata: finite state automata, push-down automata, linear bounded automata, and Turing machine. When we compare these four, finite state automata is considered as less powerful, whereas Turing machines are most powerful. Equivalence. Finite state machine is equivalent to the following: push-down automata with finite stack, Turing machine with finite tape, Turing machine with unidirectional tape, Turing machine with read-only tape. Push-down automata is equivalent to the following: finite state automata with stack, Turing machine is equivalent to the following: push-down automata with additional stack, finite automata with two stacks. The applications of different automata in TOC are explained below. Finite automata. Design of lexical analysis of compiler. Recognize the pattern by using regular expression. Use of Mealy and Moore machines for designing the combination and sequential circuits. Helpful in text editors. Use it for spell checkers. And now it's push-down automata. It is used in the syntax analysis phase, implementation of stack applications, used in evaluations of the arithmetic expressions, used for the solving of Tower of Hanai problems. Applications of linear bounded automata are as follows: used in genetic programming implementation, construction of synthetic pairs trees. Turing machines are also used for these. Use it to solve the recursively enumerable problem. Use it for knowing complexity theory. Use it for neural network implementations. Use it in robotic applications and many more. What is DFA? DFA is nothing but deterministic finite state automata. Deterministic refers to the uniqueness of the computation. The finite automata or deterministic finite automata. If the machine reads an input string one symbol at a time, they can be represented as the state by vertices. The arc labeled with an input character shows the transitions. The initial state is represented with the arrow in front of it, and the final state is represented by the double circle on the vertices. There are so many applications of DFA. Some are as follows: protocol analysis, text parsing, video game character behavior, security analysis, CPU control units, natural language processing, speech recognition, etc. etc. Now we are going to enter into our main topic, which is application of automata theory in networking. Automata are basic structure in computer science. Language equivalence, well studied, several algorithms. Application of finite automata in networking. Till now we have discussed various fields in which automata theory is used. But now we are going to discuss in specific how automata theory is used in computing and networking. Network uses some protocols to transmit and receive data over the network, and the protocols that are being used are error control, flow control, bandwidth limitation. This error control can be done with checksum and many more methods. Finite automata have several applications in networking, including protocol analysis. Finite automata can be used to analyze network protocols to determine if they to a particular standard or specification. This is important in ensuring interoperability between different network devices. Firewall rules. Finite state automata can be used to create firewall rules for network security. The rules can be based on patterns of network traffic and specify what traffic should be allowed or what traffic should be blocked. Intrusion detection. Finite automata can be used for intrusion detection by monitoring network traffic for patterns that indicate potential security threats. Traffic management. Finite automata can be used to manage traffic by directing packets to specific direction based on certain criteria. What is that criteria? They are protocol type or destination addresses. Routing protocols. Finite automata can be used in routing protocols to determine the best path for data to travel through a network. Now we will discuss the applications of these in brief. First, we'll go with protocol analysis. Finite automata can be used to analyze network protocols to determine if they to a particular standard or specification. A network protocol is a set of rules that governs communication between devices on a network. Examples of network protocols include TCP/IP, HTTP, and FTP. To analyze a network protocol, a finite automation can be constructed that the behavior of the protocol. This automation can then be used to verify that the protocol conforms to particular standard or specification. For example, let's consider the TCP protocol. TCP is a connection-oriented protocol that provides reliable ordered delivery of data between applications running on different devices, and a finite state automation can be constructed that models the behavior of TCP, including the states and transitions that occur during the process of establishing and tearing down of a TCP. Once the automation has been constructed, it can be used to verify that an implementation of TCP to the standard specification. This can be done by comparing the behavior of implementation with the behavior of automation under various scenarios and various conditions. Now we will dive into the application firewall rules. Firewalls are critical component of network security infrastructure that protect network from unauthorized access and attacks. A firewall can be thought of as a gatekeeper that controls access to and from a network. By enforcing a set of rules that determine which network traffic is allowed to pass through. Finite automata can be used to create firewall rules for network security. These rules based on patterns of network traffic and specify what traffic should be allowed or what traffic should be blocked. A firewall rule typically consists of a set of conditions that must be met before a specific action is taken, such as allowing or blocking traffic. For example, let's say a company wants to block all incoming traffic from a particular IP address. A finite automation can be constructed that models the behavior of this rule. The automation would be a state that represents the initial state and the final condition. The transitions between these states would be determined by the pattern of traffic received from the IP address. Once the automation can be constructed, it can be used to implement the firewall by configuring the firewall monitor to incoming net traffic. Intrusion detection. It is a critical component of network security that involves monitoring network traffic for patterns that include uh, potential security threats. Intrusion detection systems can be used to detect a wide range of security threats, including malware, unauthorized access attempts, and denial of service attacks. Finite state automata can be used for intrusion detection by monitoring traffic for patterns that match known attack signatures. An attack signature is a unique pattern of network traffic that is associated with a particular type of attack. For example, a signature must be associated with a SQL injection attack or a buffer overflow attack. To detect these signatures, a finite state automation can be constructed that models the behavior of the attack. The automation would have states that represent the different phases of the attack and transitions that correspond to specific activities. The different phases of the attacks may be initial reconnaissance, exploitation, and exfiltration. Once the automation has been constructed, it can be used to detect attacks by monitoring network traffic and comparing it to the expected behavior of the automation. Traffic management. Finite state automata can be used to manage traffic by directing packets to specific destinations based on certain criteria, such as protocol type or destination address. This process is known as traffic management. To implement traffic management, a finite automation can be constructed that models the behavior of the network traffic. The automation would have states that represent different stages of the communication and transits that correspond to specific actions, such as forwarding packets to a particular destination, or dropping them. Once the automation has been constructed, it can be used to manage network traffic by configuring routers or switches to use the automation to filter incoming packets. For example, a router might be configured to forward packets that match a particular pattern to a specific destination while dropping all other packets. Traffic management can be used to optimize network performance by ensuring that packets are directed to their intended destinations efficiently. Overall, the finite automata provide a powerful tool for traffic management in networking. This can avoid collision while transferring the packets in the same timeline from different sources. Routing protocols. Finite automata can be used to analyze network traffic patterns to detect anomalies and diagnose network performance issues. Anomaly detection is the process of identifying unusual patterns of network activity that may indicate a security breach, while performance analysis is the process of identifying network bottlenecks or other issues that are causing slow or unreliable network. To analyze network traffic, a finite automation can be constructed. The automation would have states that represent the different stages of network communication and transitions that correspond to specific actions such as sending packets or establishing connections. Once this automation has been constructed, it can be used to compare the behavior of the network traffic to the expected behavior of the expected automation. In conclusion, finite automata are powerful mathematical models that can be applied to a variety of problems in networking, including protocol design, intrusion detection, traffic management, and network analysis as we discussed before. By using finite automata, network engineers and security professionals can better understand and optimize network behavior, detect potential security threats, and diagnose, and they can resolve also. The flexibility of finite automata make them an essential tool in modern networking and security applications. So hereby I conclude that there are so many applications of finite automata which we can use in networking. Thank you.